Welcome, everyone. Today, we're diving into a major breakthrough that is literally rewiring the foundation of deep learning. Based on foundational research by the ByteDance Seed Foundation Model Team, we're going to explore how dynamic hyperconnections overcome the hard-coded limits of traditional residual architectures. The result? Unlocking 1.8 times faster convergence at zero computational cost. To understand this solution, we first need to understand the inescapable compromise holding back residual networks today. Deep learning forces us into an impossible choice, a seesaw effect. If we use post-norm, we alleviate feature collapse, but we aggressively reintroduce vanishing gradients as the network scales in depth. On the other hand, if we use pre-norm to fix the gradient flow, we cause deep layer features to become highly similar. This creates representation collapse, rendering those deeper layers virtually useless. The root cause of this seesaw effect is rigidity. Traditional residual connections act like hard-coded information highways. They predefine the strength of connections within a layer. Mathematically, they lack the autonomy to adjust connection strength or reroute information based on actual features. What we need is to move from these rigid, hard-coded residuals to a flexible, smart transit grid. When we evaluate these architectural paradigms, hyperconnections break this seesaw entirely. While pre-norm and post-norm rely on fixed connection strengths and static arrangements, hyperconnections dynamically learn connection strengths. This allows the network to autonomously arrange itself, achieving the gradient stability of pre-norm right alongside the representation diversity of post-norm. So, how does it actually work? Enter the dynamic switchboard. Hyperconnections abandon predefined routes entirely. Instead, the network autonomously learns the optimal strength of connections between features at different depths, dynamically rearranging layers on the fly. It achieves this through two mechanics: vector expansion, which expands the input into multiple copies to hold several historical patterns simultaneously, and trainable matrices, which replace the fixed scalar of a residual connection with a trainable matrix. This architecture brilliantly decouples the network's connections into two types, width and depth. Width connections allow for lateral crosstalk between the multiple hidden vectors within the same layer before moving upward. Meanwhile, depth connections act as vertical links, a generalized residual that dynamically assigns weighted values between the inputs and outputs of each layer. Now, you might be wondering about that vector expansion. It turns out, expanding the hidden state is an absolute necessity. If we don't expand it, meaning n equals 1, the rigid seesaw effect persists and the model fails to improve. However, expanding to n equals 4 is optimal, unlocking dynamic routing by allowing multiple hidden vectors to reserve distinct connection patterns from preceding layers. Pushing it further to n equals 8 just yields diminishing returns. We also have a choice between static and dynamic hyperconnections. Static structures learn their layer arrangements and connection weights during training, but remain permanently fixed during inference. Dynamic autonomy, or DHC, is far more powerful. The connection matrix dynamically recalculates its weights for every single token based entirely on the input itself. At an expansion rate of 4, DHC significantly outperforms the static version across all language modeling validation sets. Let's look at the performance, starting with dense LLMs. In standard 7 billion parameter dense models, DHC ensures vastly more stable training. In fact, across 500 billion tokens, researchers observed zero training spikes. It also prevents the diminishing returns usually seen after 400 billion tokens, showing a significant plus 0.293 improvement in validation perplexity over the baseline. What's truly remarkable is the asymmetric return on investment here. The overhead cost is practically invisible, a negligible 0.03% physical increase in parameters and a mere 0.2% increase in compute flops. In exchange, the performance gains are massive. Convergence is 1.8 times faster, accuracy jumps by 6 points on the ARC challenge, and it achieves 500 billion token baseline efficiency using only half the tokens. This acceleration perfectly translates to mixture of experts, or MO, models as well. Hyperconnections natively integrate with sparse architectures. By simply replacing residuals in an OLMOE model, the network achieves identical performance in exactly half the training time. And the benefits aren't limited to language. We see universal modality scaling across vision and diffusion models too. Upgrading an image classification vision transformer yields a massive 2.69% relative accuracy boost. For image generation, a DTXL model augmented with hyperconnections achieved the exact same image quality scores as a baseline model that possessed 50% more parameters. The real aha moment of this research is discovering sequential parallel duality. Hyperconnections do more than just replace a math operation, they bridge fixed architecture and neural architecture search. Because the network rewrites its own architecture autonomously, it can dynamically organize layers sequentially for deep logic, or in parallel when independent processing is optimal. If we look inside the network's mind by unfolding the connection matrix, we physically see the model learning the best of both worlds, creating a unique lambda shape pattern. On one side, deep layers repeatedly pull raw data from the bottom embedding layers, displaying pre-norm behavior. On the other, we see long-term decay, where layers learn to rely on adjacent outputs, displaying classic post-norm behavior. Ultimately, hyperconnections represent the inevitable baseline for the future of deep learning. They autonomously balance gradient flow and representation diversity without human-engineered compromises. Delivering proven performance leaps across dense LLMs, sparse MOs, vision, and diffusion models with virtually zero compute penalty, they are the definitive upgrade to the residual block. Thank you for watching.